Oh yeah, I think we'll start the session. It's almost 10:40. So yeah, hello everyone. Hopefully you can see my screen and my voice is clear. So today's session is going to be on stage math. Uh, it's a tool. It's a computational tool that people use. It's kind of an alternative to NumPy, SciPy. It's built on NumPy, SciPy, and stuff. So and it's an alternative to popular softwares like Maple and Mathematica. So um, we will look at the basics and we'll go through some more some examples at the end, and we'll understand how this tool is incredibly useful in computational problems and problems that require a lot of numerical solving. And uh, Sage Math is incredibly efficient at doing that. We'll look at everything one by one. So starting from the basics, well, what is Sage Math? Sage Math is just an abbreviation for System for Algebra and Geometric Experimentation. Uh, as modern math evolved, mathematicians found that they need some computational tool to solve most problems. So there were existing tools like NumPy, SciPy, or the Matplotlib, which is used to plot libraries in used to plot graphs in Python. And mathematicians, what they decided to do, they built a new uh, tool which encompasses all this and is more of a symbolic approach to maths and its problems. So what do I mean by symbolic? As maths evolved over the history, people started moving from words, writing stuff in words to writing stuff in symbols. For example, earlier people used to write that 3 is equal to 4 in words, and now what we do is just use the equal to symbol. So as in math progresses, uh, people started shifting to more of a symbolic approach, and an advantage of doing that in your coding program as well is that it helps you keep track of what you're doing. If the program follows a symbolic approach, it helps. It's very human-like. It can follow along very easily and keep track of whatever you're doing to it. So it's very useful to do computations symbolically, and we'll see some examples and what I exactly mean by symbolic. Um, yeah, it's an open source or free and open source software, and even my Maple and Mathematica are paid. You're paid. They are paid softwares, but Sage Math is very it's free and open source, and it's been contributed by over 500 mathematicians over all these decades. So yeah, it's a very good alternative, although it might not be as powerful and very well efficient as Maple and Mathematica. It's very comparable and it puts up a tough competition to them. So it's definitely no slouch, and we'll see how efficient it is at doing stuff. So start with some basics, and I hope you know some basic Python syntax. And if you find anything difficult to follow, just unmute your mic and let me know. I'll stop right there and then and there and explain. And yeah, so hopefully you know basic Python syntax, and we will look at how functions are used in Sage Math. And instead of going over how the functions are created, we will see what the existing functions are, and we'll try to use them in some questions and see how powerful they really are. Starting with the very basics, this is how you'll declare a variable. So if I want to work with two variables x and y, I will declare them as var of x comma y. So this declares that x and y are variables here, and it will be used as symbols. Like I mentioned here, unlike in numerical computational tools, you don't need to specify the value of the variable. It will look at it just as a symbol. Sage Math will treat x as a symbol. X will not hold any value unless you pass something to it. It till you pass a value to x, it acts as a symbol, and you can't really do that in other computational tools. And here you can in Maple and Sage Math and stuff. You can do this. So, for example, you have this. if I define the polynomial variable polyn to be x plus 1 to the 4 and I show it, it just stores it as x plus 1 to the 4. It doesn't expand it. It doesn't throw you an error saying that I don't know the value of x. What is the x plus 1 power 4? It keeps it as x plus 1 power 4. And if you notice, this is actually LaTeX. So I'm working on Jupyter. Hope you know the basic of what Jupyter is and how to run it. And I'm running a Sage Math kernel on it. If you're unsure how to set this up, just let me know after the session. I will help you out with that. So what Sage Math does is it is well integrated with LaTeX. So whatever output it is, it readily shows the output as LaTeX. And as you move on, you'll see that there are you'll see how well connected LaTeX and Sage Math are. As variables, you can just print out, for example, eta. Sage Math will recognize eta as a symbol that we usually do, and it's really powerful and it's very useful when you're writing documents and you need to uh, and you don't need to go back from one variable to another. If you have eta, you'll know that eta is this. Say it will be same in your document as well as in your code. So there is no clash of variables. It's very useful when you're writing scientific documents and stuff, and it's very powerful. LaTeX is really good, and if you don't know what LaTeX is, please go through it. It's very useful, and you'll be using a lot of it in your engineering. And yeah, even science courses as well. So if I want to expand this polynomial, what I'll do is I'll just put polyn dot expand off. What expand function does, it just expands the polynomial and shows it to you. And this dot show just latex the stuff that is output. When I remove this dot show, see what happens. It outputs it in this form. It's not very readable. And if you just add dot show and do it, it just latex the output. So it's very neat and very easy to read. Oh, I think someone has asked how to go to SageMath kernel. Yeah, I will show. Just DM me after the session. I will let you know how to do that. Yeah, and as I told you before, this thing it just stores it as x plus one to the four. Unless you pass something to it, it doesn't evaluate it. So if I want to evaluate it at some point for say x is equal to one, I will just put dot subs of x is equal to one. You just say substitute x as one, and one plus one to the four is 16, and you get that as your output. Yeah, that's pretty much it about how polynomials work and how things are saved, how symbols are saved and uh, stored in sage math. So, yeah, as in, I think I missed this. See, if you notice this, it says says the type of the polygon is a symbolic expression, and it doesn't store it as a number or a floating point value. It just stores it as a symbol. It's a symbolic expression to sage math, and it's very human like. It's very human like to see stuff as symbols rather than numbers because computers don't know symbols, they just know numbers. So when you store it as this, it's very user friendly and easy to keep track of what you're doing to it. And like I mentioned, there is a very special integration of Sage Math with LaTeX. So the symbols like pi, e, eta, delta, gamma, whatever you have, they have inbuilt meanings to them in SageMath. You don't want to mess with them and assign them another value. You just keep it as it is, and it's very powerful. So in the regular Python, you just say type of pi, it will throw you an error because you have not defined pi. Here it is actually defined as a symbolic expression, and pi. I'll just show you. Let's type pi. It will show you pi. It will not show you the 3.1415 or blah blah. It will just show you a symbol that is pi. So, and if you want to know the value of pi, you will use something called dot n of digits equal to 100. If you want Sage Math to show you a number, you ask it to numerically evaluate the symbol at some particular point. So if I want to look at what pi is, I'll just say pi dot evaluate 100 digits of pi. So it will throw me out 100 digits of pi, and it will do it for even 1,000 and 10,000. It is incredibly efficient. The algorithm is very good. It will not take a lot of time. I'll just show you 10,000 and just throws you all the 10,000 digits of pi. Yeah, it didn't even take it a second, millisecond. It's very fast. And same with E and stuff like that. Pi and E, those symbols hold these values, and regular in general they are just symbols to SageMath. They unless you ask SageMath to evaluate its numerical value, it will not give you out the value. And you can, if you want the value, you can obtain it to an arbitrary position, arbitrary number of digits, and it's very precise. There's no error in that. Yeah, like I told you, if I declare a variable eta and I show it, it just shows you the eta symbol. The same goes with gamma, delta, and stuff. So it's the syntax here is the same as LaTeX. So it's very useful. It's very useful to go back and forth between these two. And to be honest, it looks good. Everything looks good with LaTeX. So I think you should get used to this. And if you're using variables, just don't mess with this or predefined LaTeX variables. Use some other variables to while you're using a program, while you're running a program. Yeah, coming to equations, uh, as you can see, I declare an equation in such a way. So what have I done here? I've defined the equation variable to be EQ, and I assigned that EQ to be this entire thing. So notice that I've used a double equals here. So you already know that equals to is the assignment operator in Python. So if you use equal to, it just assigns whatever is there on RHS to the stuff on LHS. So you don't want to use equal to in your equations. You will have to use double equal to. So this is your x cube plus 3x square plus 3x plus 4 equals 0. That's how you input this equation to a variable. And the point to note here is that you use double equal to. Don't use single equal to. That will be the assignment operator. And to solve this equation, I'll just simply say solve of equation for x. So this is the syntax. This means solve this equation for the variable x. There are multiple variables. It will throw out x in terms of other variables. And yeah, there are three roots, two complex roots. It identifies complex roots as well. There's an I here, and it's you can see how useful this could be. It pretty much solves any polynomial equation that you throw it, and as the order of the polynomial as the degree goes larger and larger, it will take a while to compute it, but it can do it. It will do it. And another thing, most of the software that you use, for example, if you run a code on Python to find the roots, you will see that you'll generally find your roots as some floating point number. Here it keeps the root as a symbol. It uses square root 3 and stuff like that. Normal languages do not do that. If you do it in a normal Python script, it will not do this. It's a SafeMath does this, and it's very useful to see what the roots are. It shows you I square root 3 plus 1. It's very easy to visualize and very easy to work with. Instead of just throwing 1.73 and stuff and computing all these values, it just keeps it as symbols and a very user-friendly, human-readable form. And it's and you can see why this is very useful and liked by people. I would rather see, the root to be 1 plus or minus root 3 I by 2 instead of computing the 0.5 plus or minus 0 point blah 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 I. So that is an advantage to this. And there are some inbuilt functions like trigonometric, logarithmic, and stuff. They are already recognized as stage. They're already pre-built functions. So cos is just your regular cos, and the input is input will be in radians, so cos of pi would be -1, and the dot should just latex that output, so -1. And you can solve trigonometric equations as well using the same solve command. Solve sin x equals 0.5 for x. So it is 1/6 of pi by 6. And again, as you can see, it throws the output as a symbol. It throws the output as pi by 6 instead of saying 0.4 and blah, 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 blah. It just throws it as pi by 6. And it's very useful. And it is very useful. You'd rather see get the solutions to be pi in terms of pi and other numbers instead of this 0.56 and 20-digit long floating point number. So, and obviously there are the infinite roots for this, plus 2 and pi, and it's just implicit. We know that there are the roots, and it doesn't really show that. So that keep that in mind. And there is something called there is some you can simplify and reduce these expressions as well. So, for example, I have this expression cos square x plus sin square x plus cos 2x. So, what trig reduce does is trig reduce reduces the trigonometric expression as much as it can. So, it reduces it to cos 2x plus 1. It can be reduced further. So, to reduce it to the fullest extent, you would use simplify full, and this would work for non-trigonometric functions as well. This is something specific to trigonometric functions, and this is something that is general. So to do this, you see you get 2 cos square x, and trig reduces it to 1 plus cos square. And again, we can there are logarithmic functions as well. So log of 2 is just it's the natural log. So if there are other you can define other bases as well. So log 2, if I just say log 2, it just says you log 2. It doesn't show you the value again. I'm emphasizing this again and again. If I show log 2, it doesn't show you any value, it doesn't throw you an output. If you want to throw it an output, you would say, I need this for this specific position. Give me 100 digits of the output, 100 digits of what log 2 is, and it will show you the 100 digits. Then let's remember syntax is dot n of digits equal to whatever the number of digits you want. So these are 100 digits of log 2. Again, you have to call it. We don't want the numerical approximation. Say just shows you that as an expression, as a symbol. It doesn't show you the number. Again, another example to emphasize the symbolic nature. If I store this rational variable as this fraction, it shows the output as a fraction again. It does nothing to that. It's very easy to visualize this and see what you other languages don't really do this. They'll just do some slash and it's not really good. And sage math shows you it as a fraction. And when you substitute x equal to 1 in this, it doesn't throw you a numerical floating point output. It keeps it as 1 by 4. That's what you would get when you do it by hand. You don't want to compute it. You just show it as a symbol. It's just 1 by 4. If you put x is equal to 1, it's 4 divided by 16. So it simplifies that and shows you that it's 1/4, and it's very useful. And one particular case where this could be really useful is, when you calculate some stuff and calculate some huge numbers in some language, there is a limit to the precision of the number of digits after decimal that you can hold. So I think it's some 52 bits in normal Python. So beyond that, you can't really go. So can't really store the decimal digits. So what will happen is when you compute fractions like this, it will if your fraction is just 1 by 1, what other languages do is they calculate the stuff on the numerator and stuff on denominator, and then they divide it and show you that. So even if you do some calculations and finally we get 1 divided by 1, it will not show you 1. You may have seen this, it will show something like 1.00002. So here there is no such thing. It will show you the perfect one. So that's what that is the usefulness of keeping it as symbols rather than expressing it as numbers and dividing them. So you wouldn't get those errors. It's not exactly errors, and you will not get those um, slight deviations from whatever you wish to expect. So if you wish to expect one, it will show you one because it computes it symbolically, just like humans do. Yeah, and again, one point is you can do all this in NumPy, SciPy, and again, these plots can do this with the Matplotlib library. And SageMath is built on these libraries, but it's very useful. It's very math oriented, unlike NumPy and SciPy and stuff. And it's very user friendly. And trust me, you'll get if you start using SageMath, you'll never go back to NumPy or SciPy. it's that easy. It's that user friendly, and you'll see. So this is how you plot a function. If you want to plot x cube plus x, I would call the function plot, and the parameter that you pass is the function that you want to plot. Minus 3 comma 3 represents the range on the x-axis that you want the function for, and the default color of the plot would be blue. And if I want to change the color, I would just pass the parameter color equal to whatever color I want in a string. So if I want it to be red, I'll just pass color equal to string and in quotes red. So it shows you a red graph of what this function is, x cube plus x. And same. So if I want to plot sine x, I'll plot it this way. And if you want to superpose these two plots, you'll just put p plus q. If I assume this plot to be p, if I assign this plot to the variable p and assign this second plot to the variable q. So I just say p plus q will superpose these two plots and show you the output. It's very simple, and there are other things as well. You can label these plots, can do a lot of stuff like that. And there is something called scatter plot as well. You can plot, if you have a list of points x and y values, if you have 1,000 x and y values, then plot all these 1,000 x and y values on this graph, and it's called a scatter plot. It's very useful in data analysis, and you would use that when you want to fit a function to all those data points, and some explore something called regression, linear regression, and function fitting. There is actually an inbuilt function called curve fitting in this. I have not mentioned it in this notebook, but explore it if you want. It's pretty cool stuff. If you have bunch of data points, you can just fit a function through it, and you can visualize it very well as well. Yeah, moving on. Derivatives. Yeah, how do you differentiate and take derivatives of stuff here? So again, this is the way you declare variables. My variables are a, b, and x, and I define the function to be ax cube plus bx square. The reason I defined the function like this, f of x, like very humanly, Sage understands that this function, it's a function of x, it's not a function of a and b. So whenever I call f, it it knows that I'm referring to x as the independent variable here. It will not treat other stuff there as variables. So very useful. And if I don't even have to say f of x, I'll just say diff of f comma x. So what this says is if whatever function you have that you have to pass, and what you would like to differentiate it with respect to. So I want to differentiate f with respect to x, and this is the output. I can take it as well. Oh, oh, can't really. Oops. Yeah, there you go. I should be able to take this. Yeah, yeah, that is the latest output. So if I differentiate f with respect to x, you get 3ax squared plus 2bx. So it's you can see it's very useful, and there's no hassle with creating a and b as constants. You see when you say x is a variable, Sage understand that a and or whatever other variables that you say are constants, that will not uh, deal with them. It just keeps them. So it's very useful. And again, tan inverse x, differentiation of tan inverse x with respect to x is just 1 by 1 plus x square. Yeah, I'm pretty sure Maple and Mathematica are much more efficient at doing this, but this is free and open source, so it's definitely better and keeps improving over these years. But and it's no less capable than Mathematica and Maple. So when I said when I talked about var function here, it just declares all these to be variables. So when I want to deal with for example differential equations, when you have differential equation y dash plus 3y plus equals 2x something, you know that y is the function of x, y is the dependent variable there, and x is the independent variable there. What I'll say is, if I want z to be the dependent variable, I will declare it to be a function of x. So what this says is z is a function of x of the dependent variable independent variable x. So z is dependent on this independent variable. So I differentiate z. Just say that del z by del x. It just shows del z by del x. Unless I pass a value to the z, unless I pass a function to x, function of x to z, it will not evaluate the derivative. This shows it as the derivative of z. And there's a partial symbol here because in general, there may be many variables that you have to deal with. So is there may be a function of other variables as well. So in general, it does not distinguish between a single variable and multivariable function. It uses the partial notation everywhere, and it's no issue. It's consistent. It is consistent with your mathematical notations, and yeah. Yeah, we'll come to solving differential equations now. So take a look at this thing. I'll just sip some water. Yeah, so what I've done here is I declared x to be the independent variable, an independent variable, y to be a function of that independent variable, and I defined the differential equation d to be derivative of diff of y comma x comma 2. What does this mean? This 2 says that I'm taking the derivative twice. So here, when I pass no arguments, it just it is implicit that I'm taking the derivative once. If I pass the third argument, it means that I'm taking the different derivative n times. So just show you here, z comma x comma 2. Yeah, it shows the second derivative. And yeah, this means it's d pi by dx power pi. So yeah, so the third parameter is actually your the order of your derivative. So my differential equation is d square y by dx square equals minus 9y. So this is your, some of you may recognize this as your general SHM equation. So, and of course, the solution to that would be something in terms of sine and cos. And the way you solve this differential equation is using this function called solve. So what the parameters are to this function, you input the function to it, you input the what you want to solve the differential equation for. You want to solve it for y. Y is the dependent function here. So you solve it for y, and these are in initial conditions. So what does it say? This is second order differential equation. So you need to give it two initial conditions. So what this list says is, in general, the list goes like this. The first value says your value of x, and second value says your value of y. Third value says the value of y dash. Fourth value says the value of y double dash, and so on. So if I remove these initial conditions, it shows you the output in terms of these constants. So unless you specify the initial conditions, it will not solve for this constant. And if you specify the initial conditions, it will solve for a constant and show you the output. And you solve for this constant, this will be your constant, and this will be the output for it. Again, what 1, 2, 3 represent is at x is equal to 1, y is equal to 2, and y dash equals 3. And if it's an if it's a third order differential equation, our list would have four values. The values would contain x, y, y dash, and y double dash. So you need this, and if you pass, if you try to pass more variables to this, it is not exactly correct. It tries to do it, but it's not correct. If you would substitute the values, you would know, and if you underspecify it, again, it will not be able to solve it. So yeah, it throws you an error. You need again, you need to know what the order of your differential equation is, and you specify the number of uh, initial conditions that you need. And again, if some of you remember, I mentioned in this first session of differential equations that order is a very useful thing. Degree is not at all useful. So keep in mind, order is a really useful thing, and it helps you in stuff like identifying number of initial conditions that you need. So a second order differential equation needs two initial conditions, and that's what you have passed here as a list. Again, the solve of your differential equation, what you're solving for, and the initial conditions. And if you don't mention the initial conditions, it will throw you the output in terms of constants, and it's very useful. Here's a slightly more complicated example. So this is another differential equation, and I just latex the differential equation for easy reading. And dy by dx equals this huge thing, and if I solve it, you see that it throws you the solves it in an implicit way. You can't really solve for y here. This is an implicit function. You can't really find y explicitly as a function of x. It's hard to do that. Actually you can't do that. So it's really clever, and it throws you, instead of saying it's not solvable, it throws you the equation where y is dependent on x. So you can here you can actually rearrange it, but in general, if there's an if the implicit output, you can't really find y as a function of x. Sage identifies that and throws you the implicit equation. And if you want to plot the implicit equation, there is just like a regular plot here, the plot of this function. There's also a function called implicit plot. So I define this function using these variables s and t, just to not mess with x and y. So st, and if I implicit plot this function, and these are the ranges, this is how you'd specify the ranges. Uh, this is what your output would be. So this is actually, if you take a close look at it, it appears like a multivariable function, but it's not. One is a function of the other. G of x s comma t, it looks like s and t are two independent variables. It's not. One is dependent on the other, and it's dependent. So it's dependent through the equation g is equal to 0. Again, note that I've used the double equals here, not the single equals. Whenever you keep that in the back of your mind, always use double equals to whenever you're dealing with equations and you're saying some LHS is equal to RHS. So you use double equals there. And this is your implicit clause. So Sage is clever at doing this, and it identifies implicit stuff. And again, just like derivatives, you have integrals as well. So integral of, say, 2x cos of x square with respect to x. So that's how this function is. You pass the integrand as a first parameter and the variable that you're integrating with respect to as your second. And when I show the output, it just shows you sine of x square. And the reason why you do this, if there is some other variable y here, I'll have to define y. And yeah. So it does not mess with y. It understands that y is not y is an independent variable, and we're just integrating with respect to x, and it keeps y as it is. It's sort of like a reverse partial differentiation. Yeah, if you will. Yeah, again, another thing is this is very clever. It also knows that there are non-integrable, non-elementary functions, and it understands stuff like f of x. This is nothing but your error function, and this integral is actually not integrable. So integrated, it shows you the non-elementary thing that we usually define, non-elementary functions, error function of x, and this is the actual value of it. This is how you define your error function. Error function is 2 by root pi of integral of e to the minus x. It is aware of all this non-integrable thing, and again, if you want, I can show another function. Sine of x by x. I'm pretty sure that's non-elementary as well. Yeah, it throws your output as is a logarithmic integral. So it's non-elementary, and there is all it can also say define it to be SI of X, but it shows you an output in terms of EI, the logarithmic integral. So yeah, the point is Sage does integral well, and it understands some functions are non-elementary, and it deals with them through this through the normal non-elementary functions that we define in our usual sense, like error function, SI of X, EI of X, and stuff like that. And Sage understands everything, and it's very clever in doing this. Moving on, we'll actually come to arrays and matrices. Arrays are the same as matrices in a sense. So if you want, this is how you define a vector and a matrix in Sage Math. So B is a vector of 1, 2, 3. So what it means is the components of these vectors are 1, 2, and 3. It's a 3 cross 1 matrix. A vector is just a column matrix, right? So it shows it as 3 cross 1 matrix, but actually, uh, I'll show you. When I try to see what B is stored as, it's stored as this tuple. It stores it as 1, 2, 3, but don't be confused. If I show the type of V, notice that it's not your tuple, it's a vector, it's some vector stuff. So there's actually a difference when you define something as vector of 1, 2, and 3 and something as a tuple of 1, 2, and 3. And if you try to operate matrices and vectors on the tuple, it will not work. You will have to pass it on as a vector. So if you just simply pass V as open parenthesis 1, 2, 3 close parenthesis, it will not recognize it as vector and it will not do calculations with it. For Sage to understand that it's a vector, you need to specifically mention that it's a vector using this function. So yeah, and you can calculate stuff, the product of matrices. You just use a star operator. Star means the matrix is uh, being multiplied with this matrix. Yeah, so why is A star B? Is the output Y. Yeah, it doesn't. Yeah, A star B, A multiplied this 3 cross in matrix. So this is how you pass a matrix to Sage, and I'll show you the matrix as well, how it is stored. Yeah, this is stored as so. So this is the syntax for assigning a matrix. The first list would be the all the numbers in the first row. The next list would be all the numbers in the second row, and so on. And this could be of any shape. It could be a rectangular matrix. It could be any arbitrary enclosed matrix. And again, for you to multiply, you need to remember stuff like the order. You need to keep in mind the order of the matrix so that the multiplication makes sense. So sure, your vector is the three cross one matrix and your matrix is 3 cross 3. So A star B makes sense. It's a 3 cross 3 times 3 cross 1 matrix, which will give you a 3 cross 1 matrix again. This is a vector. And try doing this by hand, you will see get the same output 14 when you operate this matrix on this vector. So yeah, matrix multiplication is just as simple as putting a star in between. And and these are your standard functions. Eigenvalues. If the syntax is your matrix dot eigenvalues of. So you just pass for the matrix A, the eigenvalues of 5, 0, and -1. You can verify that. And if I want to find it also does row reduced echelon form. And as you can see, this is not exactly row reduced because the determinant is actually 0 here. And yeah, it's evident from the eigenvalues as well. One of the eigenvalues is 0. So the determinant is also 0 and it's non-invertible. So you can't really get identity matrix as your row reduced echelon form. So it just stops it at this point. Doing calling some other matrix, again a 3 cross 3, another 3 cross 3 matrix, which is non-singular now, just to show. And if I find the RREF of it, you can see that it gives you the identity matrix, shows that the determinant is non-zero and an inverse exists for this matrix. And this is a regular 3 cross 3 and 3 cross 3 matrix multiplication. It gives you a 3 cross 3 matrix again. And this is how it calculates the inverse of a matrix. The function is in this inverse of. So B dot inverse of gives you the inverse of B. And again, see that it shows it as fractions instead of floating point numbers, something like minus 0.33333. And it shows it as a fraction. And it's very easy to now work with this. And if you want to work it by hand from this point, you can just retrieve the fractions instead of trying to deal with the floating point numbers. Yeah, and that's pretty much about all the basic stuff in matrices. And there are other stuff as well. You can define a vector space. You can find its basis. You can find its dimensions. You can do all sort of stuff with it. But for now, you don't need much of that. These are the basic stuff that you need when you're dealing with matrices. Moving on, this is all about the functions, all about these different functions that are available, and these are more than enough to start solving stuff and creating models on stage. So I'll show you an example. I'll show you two examples, one about differential equations and one about matrices and how powerful your solution can be with just these basic functions. The questions are not very out of the world. It's quite easy, and you'll see how easy it is to solve it with same. I'll not go to the solution. Just read through this question. I'll give you just a minute. Try reading through this question. It can seem quite daunting at first, but the question is pretty straightforward. I'll give a few more seconds, just go through it. Yeah, so hopefully you went through it. If you didn't understand it, I'll just try to put it in a very simplified way. What you have is you create this 100 cross 100 square, and there's a circle inside of it. And what is happening is this you're creating a model that mimics what it would be like keeping a hot circular plate of radius 25 on a cold surface, on a cold 100 cross 100 square surface. So if you keep a hot plate on this cold surface, what would happen? So what essentially happens is the heat diffuses and goes to the environment. So if you how do you simulate that in how do you even simulate that? So the way you simulate that is you assign each point on a 100 cross 100 square as a node. You call that node, for example, t of 3 comma 4 means the 3 comma 4 coordinate. It represents that node. So what I'm basically doing it is I'm splitting this 100 cross 100 area as 10 power 4 points, 10 power 4 nodes. So each node there will be a specific temperature value, and the starting temperature value can pass the starting temperature value is given by the circular region, all the nodes in the circular region. The square plate is at zero temperature initially, and the circular disk is at some random temperature. Uh, it's very hot. So what you'll do is assign all the nodes that are inside that circle to be some value and all the nodes outside the circle to be zero. We can store all this data as a 100 cross 100 matrix. So each point or each element of the matrix will represent the temperature value of that specific node in your plate. So uh, this is your general, the thermal diffusion equation. This is the Laplacian of T equals 1 by alpha square times the partial derivative of T with respect to time. I don't You don't have to worry about this much. And basically, when you discretize this equation, what you get is this differential equation. It's a differential equation, as you can see. So it's something called a central approximation. It's a central approximation to a second order derivative. So what this differential equations say is how the heat diffuses through. That is how the temperature of all these nodes change with time. So this lambda here, it's just something dependent on this alpha, the physical conducting properties of the disk material. And if I discretize these points as, in real world, everything is a continuous spectrum. So in you would it's much more apt to deal with derivatives there. But to simulate something like this in general, we will discretize it as a huge number of points, that is 10 to the power 4 points here, and we'll assign each we'll describe the differential equation in a discretized way. So instead of saying something like a f of a plus h and f of a, I'll just say tm plus 1 and tm. So tm plus 1 comma in uh, at the m comma nth node, what happens is the temperature value changes, the new temperature value after time delta t for say 1 second. It would be this value plus some lambda times the t m plus 1 comma nth value, the node to the right of the our m comma nth node, plus the temperature value of the node to our left, plus the temperature value of the node below, plus the temperature value of the node above, minus 4 times. This is something like taking the average. You can think about this as or the average of the surrounding four nodes all at point. So uh, and for boundary points, these are special conditions, and you don't need to complicate it. You just can assign the neighboring value to the boundary points, and if you do that, uh, you would get something like this. So this is your disk, and this is your 100 cross 100 plate that you're keeping the disk on, and this black circle that I drew here, this is your disk boundary. So initially the plate is very hot. This is a scale that shows, and the surrounding is very cool. And as time passes, as a number of iterations go, uh, the heat slowly diffuses, and you can see it just diffuses very symmetrically and the way you would expect uh, in a physical in a physical world. So this is how heat actually diffuses through a disk if you keep it in a surrounding, square plate. And this is for particular zero point 0.2. I made all this for lambda equals zero point 0.2, and this is the code for it. I don't have much time to explain the code. I will share the notebook and go through it. What it essentially does is, as you can see, I have set up the array. So the array holds the value of all the temperatures of each node, including all those boundary conditions and all. And what this function does is, I'll pass through the lambda value and number of iterations. What the iterations mean is the time, the number of, as the iterations are more and more, it just says that more time has evolved. So it's just a placeholder for time. When you're dealing with discrete values, again, as I said, this is how your uh, new temperature value is defined. So, for example, after 1 second, this is your new temperature value. So, what this would mean is, after if I pass iterations as 1,000, it would mean after 1,000 seconds, you would, after doing this calculation on 1,000 times for all the 10 power 4 values, this would be the set of this array. The array would change like this, and the new array would hold the temperature values after those 1,000 seconds or those 1,000 iterations. So yeah, so I've defined this function. It's just a couple of for loops, and it's easy to understand. I encourage you to go through this, and if you have any doubt, just let me know. You can always ask in the group, or You can even DM me. And this is how you would plot this stuff on this. I've defined the I've defined the figure and axis. These are some stuff so that if you don't mention this, it will just show you a huge diagram, and you don't want that. So these are some other parameters that are useful when you are plotting something. So you have your axis, you have go through all this, and this CMO thing is just a thermal map, and I've imported it through this. Don't worry about this much. There are other inbuilt maps, heat maps as well. So what this map is, if you have an array of values, so what it does is, at it sees the array, and for example, your array has values from -5 to 10. For example, 3 cross 3 array has the values 1, 2, 3, -1, -2, -5, 2, 4, 8. So all these values are between -5 and 10. So what this color maps do is they assign a spectrum of colors to all these numbers. So as the number becomes larger, it assigns a lighter color to it. It's a hotter color, a yellow. And as the value goes down, as it approaches -10, it assigns you a dark color. So it's the same as the temperature, temperature values in a physical sense. So when you do it's very, as you can see, if you want to visualize some uh, physical area as and visualize its temperature, you just put it in a matrix. Each element of a matrix would mean it would represent the temperature value at that specific node, and if you just put a color map through it, it understands the spectrum of values, and it will assign up a very good color scheme like this, so for you to understand the intensity distribution of the values in the matrix. And yeah, this is what you would get. uh, Try this out, try this for other values of 0.2. And if you notice, there's a question here: what happens if you choose a large number as lambda? So as I mentioned, this lambda is something dependent on the conductivity properties of the material 1 by alpha. So in our physical world, we are limited by some specific alphas and so limited by some lambdas. When you go beyond, when your lambda is not in between 0 and 0.2, put some lambda 0.5 or put lambda as 10 and see what happens with this part. It will show you some absurd simulation which is not possible in real life. So try that out. Mm, That's about. I'll share this notebook, and if there is any doubts, you just ask me, and play around with this code, and uh, change the number of iterations, change the number of lambda, and see what happens to the diffusion. Again, one more example, and with this, I think we'll conclude this session. So convolutions. So what is a convolution? Convolution is nothing but when you have two matrices, you just operate one matrix on others. So it's like a function. So what this function does is it takes two matrices as inputs, and it does this operation that this GIF shows. So what this GIF is showing is this small matrix. This is called your kernel. So what this kernel does is it it loops through all the elements in your bigger matrix and in your parent matrix. And at this instant, you can see this 3 cross 3 matrix operates on another local 3 cross 3 matrix. So what it basically does is at each point, it evaluates the element wise product and puts that as an output here. So if this is an n cross n array, you will get an n minus 1 cross n minus 1 array in this, because you have to deal with boundary points, and you will start right from here. That's how your 3 cross 3 kernel operates, and 1, 2, 3, 4, and you will go through all the values in this, and each value on the output matrix just represents the element wise product of this two matrices. What do I mean by element wise product? When you have your usual matrix multiplication is a bit different, right? You take this first first row, first column element and multiply first row, first column element, second row, first column element, and so on. But here is just a normal multiplication. Like it's just element wise. You multiply the first element with the first element and output it as first element. Second element with second element. Third element with third element. It's called your element wise multiplication. That's what it's also called the Hadamard product. That's what is going on here. So why are convolutions useful? When you traverse through a matrix like this, and uh, for your usually your images that you deal with, images are nothing but arrays that hold RGB values. So images are made of pixels, and each pixel is just a color which is represented by a particular set of RGB values. And these RGB values are stored as some numbers. It can There are multiple formats and multiple ways to store the numbers. There are in some ways you can store it as a value between 0 and 255, and in other cases you can there is a format called RGBA. So in that you would store the RGB values as some three values in between 0 and 1. So one R value in between 0 and 1 G value in between 0 and 1, and one blue value in 0 between 0 and 1. And each of these values, each of this set of values will give you a particular color. So 100 would be your red color, and 0 would be a green color, and so on. And if you want a mix of colors, you specify each value of this, and fundamentally, you can describe any color with these three RGB values. So your matrix, your image is just nothing but a matrix which holds these RGB values. Just like in our last example, our matrix held all the values of the temperature. So in an image, the matrix just holds the RGB values, and it shows. Then each pixel gives you a color, and as a whole, the you will get an image. So when you apply this when you apply a particular kernel to these images, you get some effects in your output image. So for example, if you want to do something like blur your image, you can pass a specific kernel, and if you convolve it with your image matrix, it will blur the output. And how exactly it does that, uh, I can't really cover that in such a short amount of time. There is a nice video by Three Blue One Brown on this, on how convolutions work, and I encourage you to go through that. And this is a question. So this is how this convolution operation is defined mathematically. It traverses through all the elements, all the non-boundary elements of this matrix, and it just outputs the element-wise product in the new matrix. So when your kernel is this oddly specific matrix, this actually blurs your image. When you operate this when you operate this kernel on your image matrix, it produces an effect of blurring. So and this is an example. And if I pass this left image through this as a matrix, and if I convolve it with this kernel, I get this output matrix, and you can see it is slightly blurred. And why this why does this particular kernel do that? It's You can try to think of it as see uh, what this thing does is it reduces the neighboring values effects, and it increases the increases the contrast of your pixel that you're dealing with it. So what this essentially does is it brings you out of focus. So getting out of focus is the same as blurring. So blurring essentially means you're getting the image out of focus. So what this does is it slightly brings each pixel out of focus, and this 1/16 is just there to normalize everything. Like I said, RGB values can only be between 0 and 1. So when you do this, you will get some value just not in between 0 and 1. And 1/16 just normalizes that and brings it down to 0 and 1. So yeah, it might sound a bit vague now, but I would highly recommend you to go through and explore more on this. And brightness, it's very simple. You just multiply each pixel value by some amount x. So depending on what an x is, it either brightens up your image or it brightens down your image. So where x is greater than 1, your image actually brightens up, and if x is less than 1, the image brightens down. So here is what they look like. When your x value is greater than 1, you see the image is brightened, and when your x value is less than 1, it is toned down. So how do you write a code for something like this? It's very simple. Here is a pseudo code for it, and you just take an input image. That image would hold RGB values. Split the RGB value into three matrices, and each matrices would contain the R, G, and B values respectively, and create a convol function that performs this convolution operation that is defined here. So this is element-wise multiplication, and do that to all these three matrices, these three R, G, and B matrices, and after the convolution operation, combine all these three matrices into one single RGB matrix again, and output that RGB matrix, which is essentially your image. So as you can see, it could be very difficult to deal with images in general. But if you think of images as just a matrix that holds values, you can do a lot of stuff with it. Stuff with it. It's as simple as that. And for boundary points, just ignore the boundary points and don't worry about them for now. And I would want you to try out this code and try out this thing and. Uh, it's not a task, it's not a question for your assignment, it's just something out of pure interest. So if you're willing to do, just try doing this, and I'd be more than happy to help you out if you have some questions. So after this session, just DM me anytime you want, and I'll help you out with whatever you want, whatever doubts you have with this. And yeah, this is your pseudo code. Try doing and try writing a program using CH math. And if you notice, I use NumPy and SciPy here. And for this first question, and you can use this CH math as well. I encourage you to do that. All these NumPy functions have a corresponding CH math function as well. So, and it when you do it with CH math, it is a lot more cleaner and easy to see. So try doing that. It's a very good exercise. And yeah, this is another question that you can try. And this is pseudo code. I'll share this notebook. And if you have any doubts, just feel free to ask me anytime or ask anyone in the group. So, yeah, that's about it. You won't have any questions on this session. It's just something out of pure interest. And one thing that I would like to mention is this was actually inspired by that course that we had in IIT Madras. So we have this course called Scientific Computing. We usually first years have it. It's an alternative to CS course. So this is where I learned all this. And if you are a fresher who's just joining IITM, just highly recommend you to choose that course if you can. And yeah, it's a very useful course. And stage math is something a lot of people are not aware of. So if you're able to do this and learn LaTeX as well, try exploring it. And I'm pretty sure it will help you a lot when you're trying to do something, when you're trying to write some research summary or I don't want to say research paper, it's very difficult. And if you want to write an article or something on math or science, it's very useful to know these tools. And I hope I introduce you to Sage Math well enough for you to start exploring this and start working on this. Just basic Python syntax with these extra functions and some other syntaxes for these functions. And yeah, I hope you learn something through this and explore more on Sage Math if you can. And yeah, this wraps up our summer school. And I think you have a test now, so good luck for that. And yeah, feel free to DM any of us for any doubt. We can discuss this coding and coding stuff or math in general. Feel free to do that. And yeah, good luck for your test and keep working. Oh yeah, like I said, this is not exactly a compulsory session, just a fun session that we wanted to do. There's no attendance and all, and hope you learned something in this session. Yeah, that's all I really want. Yeah, and look, good luck for your test.
Hello guys, I will be sharing the Google Form link for the test. The test will be beginning in 1 minute. Uh, so I'll share it at 11:45.